Now that we have all of our subsections defined, we can put all of these parts together as one. Here is the circuit diagram for our full design. Our photocell is set up as a voltage divider with a 10K resistor and its output feeding into analog input 0. Remember that the photocell has a resistance that is inversely proportional to the detected light, or as light goes up, resistance goes down. So a high brightness environment would make A0 more connected to 5 volts, which means increasing brightness is proportional to the voltage seen at the analog pin. The humidity sensor circuit has one data line with a 10K resistor pulling up to 5 volts. This makes the data wire sit normally at 5 volts, and when a device wants to send out a binary 1, they digital write low to force the wire voltage to ground. The microSD card section is straightforward. Pins 11, 12, and 13 on the Arduino are dedicated for SPI, and pins 9 and 10 can be moved to different pins if desired. If the system used another SPI device, DI, DO, and SCK for that sensor would connect to the same points as this circuit, but the new device would need its own CS or chip select pin so that only one sensor is listening to the data pins at a time. Our barometer has the capability to use I2C or SPI to talk to a host controller. Here we're using I2C so the sensor communicates through SDA and SCL on the Arduino. It can be difficult to know how the system is performing without any kind of visual feedback, so we have two LEDs to let us know how things are working. A power LED to let us know that the system is receiving power, and an activity indicator LED connected to one of the digital pins. We'll turn on the LED when the SD card file is opened and turn it off when it finishes writing so that we have a visual indication that the recording program is working fine. Here's the circuit on the breadboard without any Arduino connections. We have a 5-volt line to everything that needs it, and a ground, and here are the data connections to the Arduino. Here's power, here's the SD card connections, and here are the I2C connections for the barometer. This bundle is for the photocell, the DHT, and the activity indicator light. Here's our empty program with our previous programs opened in other panes. When I write programs that use multiple devices, I like to have extra panes open showing either demo code or libraries so I know what tools are available to me in the main program. Let's start the file by including all of our libraries at once. Create an instance of the BMP280 library called BMP, used to access the sensor's library functions. Do the same for a variable called DHT for humidity. Note that the BMP initialization doesn't have any arguments, but the humidity library takes the pin number and the DHT type, which could be DHT11 or DHT22, a higher version of the same sensor. Create some integers for photocell and indicator light pins, and create the set of variables for dealing with the SD card. We want to track time, so let's make an unsigned long variable called timestamp. Making this variable an unsigned long type allows the timestamp to count to a very large number without restarting back at 0. Now let's make the variables to store our data before dumping to the SD card. The delay is just so that we can quickly change the logging delay without having to change the meat of the code. These are float variables so that they can represent fractional values like 3.14 as opposed to int, which can only represent whole numbers. In our setup, start by beginning our serial port, then set our pins to their pin modes, and set the LED pin to off right away just to make sure it's off. Check if the BMP280 is active, and then configure it. Initialize the SD card and open the log file so that we can print the first line of the log file, which is going to label the data. This is called the header. Close the log file, and don't forget to handle a log file failure. At the start of the loop, let's double check to make sure the SD card is still inserted. Then read from our sensors and store their data. Average the temperatures. Now that we have all of our data, let's open the log file for writing. We need a few log file.prints separated by commas so that they can align with our header line. And the last bit logged should be the output of the millis function and a new line character to prep for the next line of data. And close the file now that everything is logged. Just so that we can tell what the system is doing, let's turn on the indicator light right after it checks if the log file is opened, and turn off the light after the file is closed. This will mean that every time the indicator light blinks on and off, it has logged one line. Add a delay just so that we can freely control the delay if we want. I forgot to copy over the declaration for the initialize card function, so let's copy that over from the SD card demo. Let's upload this code so that we can test it. The initialize card function at the start of the loop will make the Arduino wait for the SD card to be inserted. So let's insert a card to start recording. The power LED is glowing bright, so we're good there, and the green activity indicator is blinking pretty quickly as it logs each line of data. We can see that every now and then the light takes slightly longer to flash back on. I think this is due to the humidity sensor having a long refresh rate. If we take out the SD card and check its contents, we can see all of the data just recorded. If anything was wrong with our program, we would have seen the compiler tell us, the file wouldn't exist, or the data would be jumbled or non-existent. If this is the case, make sure all the pins are initialized correctly, log files are being closed, make sure all the wiring is secure. A flimsy wire connection could mean that one of the sensors are getting completely disabled. If we load up this file into Glue and make a scatter plot, we can examine the trends in the data. A good test for a system with lots of sensors is to run the system and stimulate each sensor one by one, and confirm through graphing that each one responded appropriately. Here we can switch what is displayed on each axis, and we can choose from any of our datasets. Now let's find out how much power the system is consuming. Here we have the analog discovery scope providing 9 volts for the Arduino, and the meter is connecting to the ground terminal from the DC jack to ground on the supply. This way we can measure the power passing through the whole system. We can see the system consumes a little over 50 milliamps without the SD card, and with it the current fluctuates with peaks as high as 79 milliamps. Since we have the actual power consumption of the system, let's find out its approximate battery life. We'll assume an average 70 milliamps, and our top choice for a battery was a 9-volt lithium battery with 750 milliamp hour current capacity. If we take capacity and divide by current consumption, the only unit left is time in hours, which should be our approximate lifetime before power failure. This gives us around 10.7 hours of runtime, well above a hypothetical 3-hour flight. If all we need is 3 hours, then multiply that by 70 milliamps and we get 210 milliamp hour minimum capacity for our battery. Looking at the alkaline battery, we can see that even at high current draw, the cell has enough capacity for the system's needs. If we do the same equation as above, we get a 5.7 hour runtime from the alkaline's 400 milliamp hour capacity. This would give us enough time for recording the flight, data while on the ground, and some verification tests just before launch. If the batteries were being thermally insulated, either of these units would be a good choice, though the lithium being lighter still has its benefit. There are other aspects of a flight that are useful to understand when designing a system, so let's have a look at some data from a previous flight to get an understanding of what our system must be prepared for. I've loaded up a file from a prior flight. Let's create a scatter plot and look at the pressure and temperature data. Right now, we just want to know the max and minimum temperatures seen. Here we can see the lowest temperature measured was -40 degrees Fahrenheit, and the lowest pressure recorded was around 1500 pascals. If we compare this to the datasheets for our sensors, we can see that this is actually colder than this particular humidity sensor can handle, and we'd expect a lower limit cutoff at 0 degrees C or 32 degrees Fahrenheit. The BMP datasheet says that we're right on the edge of its temperature limit at -40 degrees Celsius and a pressure lower limit of 300 hectopascals, or 30 kilopascals. This means that while it might be capable of measuring most of the temperatures seen during a flight, it can't detect pressures as low as the ones seen at the peak of this flight. If a particular flight happens on a colder day, then the temperature swing could dip lower than the sensor's cold limit. A proper design should have parts that are capable of handling these kinds of extremes. Any design chosen should have detection and operating ranges that are compatible with a flight, and care should be taken to make sure parts don't get too hot or too cold. Let's go back to our graph so we can find out more about what happens during a flight. Change our x-axis to millis, and change our y-axis to altitude. This chart now shows the payload altitude over time. If we zoom into the different parts of this chart, we'll find that the flight duration is around 2 hours, 15 minutes, and 30 seconds, with a peak around 98,000 feet. Let's pull apart this chart by creating colored subsets to identify the different portions of the flight. I use the convention blue towards the sky and green towards the grass to identify whether or not the payload is rising or falling. Zoom in to get the areas near the transitions, and we'll add another subset for the data points at the peak signifying the balloon popped. With our subsets defined, we can uncheck the raw data box to hide all the data points with the payload just on the ground. Now if we change the axes to pascals and altitude, we can see that there's a smooth pressure curve going up and the trend is mostly the same going down, aside from some noise probably caused by the wind blowing past the sensor as it tumbles through the air towards the ground. Graphing temperature against altitude shows some slightly different results. While the pressure measured was almost the same going up as going down, the payload instead gets coldest on its way up and after a point begins to warm. After the pop, the payload is now holding some extra heat energy and it retains it as it descends, keeping it warmer than on its way up. Let's dig deeper and create a 3D plot to see the flight from another perspective. Minimize this window and drag the dataset into the main area, but this time choose the 3D scatter for the plot type. Now let's change the vertical axis to altitude and the horizontal axes to pressure and temperature from the DHT22 humidity sensor. From this angle, the space looks like the pressure versus altitude chart, and from this angle, it mostly looks the same as the temperature chart. The main difference is that the temperature shown earlier was from a thermocouple, a standalone wide-range temperature sensor, and this data here is from a DHT22 that dips into a colder region than it can handle, as shown by the flat regions. Let's have a look at how turbulent a flight is. Let's change the horizontal axes to some horizontal accelerometer data. Here, the blue region representing traveling upward has very little horizontal acceleration, and mostly sits around 0. However, after the pop, the payload appears to experience almost 4 Gs of acceleration in random directions. This makes sense because a balloon pulling upward would be the main force acting on the payload up to the pop, where the payload tumbles until it reaches thicker regions of the Earth's atmosphere. This is where the parachute starts to catch the air. If we switch to our gyroscope sensor showing rotation data, we see similar results, a steady rise and a violent fall. Since the rise is so much more stable than the fall, it might be favorable to plan an atmospheric experiment to be executed during ascent. Let's isolate the rise and see if there are any other interesting events in that data. Let's check out what a visible and infrared light sensor saw during the flight. Here it looks like both visible and infrared channels experience a lowering light intensity at a similar time, though the rate of change between brightness and darkness is slightly different. I want to look a little deeper at this pattern. Since we're mostly only looking at one color dataset, we can try using a varying color to act as another graphing axis. Click here and change the color from fixed to linear. And then just for visual clarity, I'll use this color scheme. Viewing our scale, we can see that the brighter red corresponds to a high UV intensity, and pale yellow or white represents low UV readings. Here we can see a slightly higher UV intensity incident around the same time there's a complete drop in infrared and visible light. Without a high data capture rate, sensors chosen based on the environmental requirements and sturdy physical design, this optical event might not have been captured very well, as it's an event that only lasts a couple minutes long. When designing a real payload, always keep in mind what the experiment is and what its requirements are, so that when its data is recovered, it can actually be useful for answering the experimental question. Try to predict what could possibly go wrong and cause the system to fail so that you can design against that. There are 2 more pieces left of this video series: Control, where I'll talk mostly about what is a controller and what kinds of options are available and why one might choose those options, and Polish, where I'll show you how to make a payload design into a physical PCB using Eagle, and other things to consider when building physical parts for a system like this, like housings. Thanks for watching.